Welcome back to the channel. Today we're going to finally take a look at one of the videos that I've been wanting to make for a very long time, and that is basically to look at biomolecules, and we're going to start with the very simplest, and that is a polymer. So we're actually going to take a look at the simplest polymer, polyethylene, and we're going to make a very straightforward chain, but we're going to take a look at how the atoms are arranged, how we might generate them in a efficient way, and how we can write a data file in LAMMPS to actually write out all the information you would need if you're going to model all of the explicit bonds that you might want to do, depending on the type of potential that you're using. Some types of potentials, and you can look at the potentials video I made, some types of potentials don't actually need all of that bond information. They just are able to calculate the right structures just based on atom positions. We're going to take a look at the explicit bonds because this way is more complicated on the generating the data side. The potential themselves are much simpler, but the input data is much more complicated. So let's take a look at polyethylene, and let's look at what that structure is and how we might generate it. So first of all, if you're watching this video, you likely know a lot more about polymers than I do. My research is mostly focused on metals, but if you don't know about polymers, I'll give you a quick tutorial. Basically, a polymer is a very long molecule. It's basically an extended chain of different individual molecules or a monomer. So it's a long chain of these connected molecules that can extend and squiggle and essentially spaghetti and fill up a space. Sometimes they're spaghetti, sometimes they're crystalline, and then there's a lot of different types of connections that can go into them. But basically it is a very long chain type of molecule. So the one we're going to look at, polyethylene, is as simple as it gets. It's just carbon and hydrogen, and there is 2 hydrogens for each carbon. And basically how that works is you have a carbon, and then there are 2 hydrogens on top of that. See if I can get that right. There are 2 hydrogens on top of that, and then you take that whole structure and then you duplicate it and flip it 180 degrees so that you have another set of them. And so these two carbons and these 4 hydrogens make up the basic structure, and this is the repeating element that you find in polyethylene. So let's just take a closer look at what that looks like and see how to generate it in code. Alright, so to write this data file, I'm actually going to use a scripting language type of code called Julia. If you haven't heard of it, I really encourage you to take a look at it. It has a lot of interesting qualities that are actually really good for writing this type of code. But I'm not really going to go into any detail about it in this video. If you want to see a video with that, I'd be happy to make one, but there are a lot of videos out there that cover Julia pretty well. So I'm just going to focus on the code that generates the atom positions and all the other information that we need. And it's very readable, so you should be able to translate it easily if you want to write it in Python or MATLAB. So that's the disclaimer, and with that, let's just get right into it. So I'm going to start out by defining a couple things that I'm going to need to actually build my structure. And the first one is the angle between the carbon-carbon set. So that angle that goes kind of back and forth as these chains, as these molecules are chained together. And so that angle is actually this 109.5. For the rotation matrix, we actually want kind of half of the half of the other angle in the triangle. So that's why I do this 180 minus 109.5. And then I convert it into radians because that's how it works. And we're actually dividing it by 2 because we're rotating it first one way and then the other. So I'm going to turn that into a rotation matrix right here. So we're going to rotate this around the z-axis. So, we're just kind of planning out ahead. We're doing this, we can literally do whatever we want here. We're making it. So I decided that we're going to make this chain run in the x direction, and the z direction is going to be the plane that is created by the carbon atoms as they zigzag back and forth. They're all going to be the normal is going to go in the z direction. So they're going to be sitting in the xy plane. So we're also going to need kind of a mirror matrix because our hydrogens stick out to the side, and so they'll flip first one way, then the other. So we set up one for that. And we're going to need a rotation to rotate the two hydrogen bonds out of that XY plane. And so they're just a 60-degree up, 60-degree down. So we can set that up very easily. Final pieces of information that we'll need is the carbon-carbon bond length and the carbon-hydrogen bond length. So I just store those so that they're in one place and we can modify them easily. Okay, next thing is to actually set up storage arrays for all the different data that we'll need. And we'll get into a little bit more of some of these as we actually create them. But basically the 5 things that we'll need to store is atoms, types, bonds, angles, and dihedrals. Atoms and types are pretty self-explanatory. So are bonds. I am going to store 3 different numbers to keep track of bonds though. The first is going to be the type of bond, and then the second 2 are going to be the indices of the atoms. That type of bond basically refers to, are we looking at a carbon-hydrogen bond or are we looking at a carbon-carbon bond? So that's just, I'm going to store it right there so it's easily accessible for me. And we'll talk about angles and dihedrals as we get to them. All right, so as I mentioned, we're going to make this chain head in the x direction. So I'm going to set that up as a vector right away. And we're going to create our first atom, and just for ease, we're going to create it right at the origin. And this is arbitrary, but we've decided that carbon is type 1, so we add this 1 to the type array. Our second atom is going to be our first hydrogen, and so I rotate it out of the xy plane with a rotation of 60 degrees, and add 2 to the type, and then we have our first bond. So we're calling this a type 2 bond. That's a carbon-hydrogen bond, and it's between atom 1 and atom 2. Similarly, we add our second hydrogen. Notice this one is being rotated above the xy plane, and this one is going to be rotated below. And then we add another bond that's between the first atom, which is our carbon, and the third atom, which is the hydrogen we just made. And it's also a type 2 bond because it's a carbon-hydrogen bond. Finally, we need to store this angle. And basically this gives LAMMPS a way of controlling how the angles of these things, how they get controlled. And so we store these by storing 3 indices. The indices at one end of the angle, the index at the pivot point of the angle, and the index at the other end of the angle. So with our carbon-hydrogen-hydrogen that we just made, that's going to be hydrogen, carbon, and then hydrogen. So 2-1-3 or 3-1-2. So with that, we've created our first carbon-hydrogen-hydrogen set. And so now we just need to go and create, many more of them. So I decided I'm going to make a 30 atom chain. So it'll be 10 sets of these carbon-hydrogen-hydrogens. And we just iterate. So I keep track of the number of atoms with this I. And then these 2, I actually transpose the rotation matrix at the beginning every time so that it flips back and forth each time, because I'm going to be doing this kind of back and forth type of creation. So I want to make sure that I'm mirroring it every time. And so I'll just do that at the beginning of the loop. And then we start adding our atoms. So first we'll push the main carbon of our CH2, and we just take the atom position -2. So this is the carbon that I made last loop, or in the first case, it'll be this atom, and we're going to move it relative to that atom. And so we're going to add the carbon-carbon length, rotated in the right direction, and in that chain vector direction. That chain vector direction rotated into the right direction and scaled by the right length. It's an atom of type 1, and it has a bond with the carbon that I made, so that index is whatever I is -3, and whatever I is now. So those are the two indices in that bond. And it's a type 1 bond because it's a carbon-carbon bond. Now, if I've already created at least two other carbons, then I also need to create a carbon-carbon-carbon angle. And so I'm going to store here. So it'll be I-6, I-3, and I will be in those carbon-carbon-carbon angle. If I've already created 3 other carbons, then I store what is called a dihedral. And essentially a dihedral, you can kind of think of it as how the chain is twisting. So I showed you earlier that the set of 2 CH2s, the C2H4 if you will, and it had hydrogens going up and hydrogens going down. Now, once I have 4 of those, I have 2 sets. So I have 4 carbons and I have 8 hydrogens. Those 2 molecules, those 2 C2H4 molecules can be at some angle relative to each other so that the chain is kind of twisting. Most chains won't actually naturally twist, at least most like plain carbon chains don't naturally twist. So you actually use this dihedral to keep those those consecutive molecules from twisting, or at least put some force there that makes them resistant to twisting. So that's what this does. It gives us a way of controlling that kind of twisting along the chain. All right, so then to store that, we need whatever carbon we created 3 loops ago, so I-9, I-6, and I-3, and then finally I. And so we store those 4 indices. Finally, we can get to creating our hydrogens, which is just the same as we did before. We have our chain vector, so that's kind of the direction that we're going. We rotate that by 90 degrees, so we're coming off to the side of the direction that we're going, and then we rotate it above the XY plane, and we scale it by the carbon-hydrogen bond length. Similarly, for the second hydrogen, we rotate our chain vector off to the side again, and then we rotate it below the XY plane, so I've transposed that rotation matrix, and again scale it by the carbon-hydrogen bond. And for the first hydrogen, we stored a bond, as well as for the second one, and then for the second one, we actually store that angle just as we did outside of this loop up here. So again, we store the other hydrogen, the carbon, and then this hydrogen as that angle. And so if we just loop through that as many times as we want, then we are creating this very straight polyethylene chain. Now, I did something fancy, if you will. At the very end, I've decided to connect the last carbon I made with the first carbon I made. So this index 1 with this however many atoms I made minus 2, so that's the last carbon, and I've connected those. And I did that because I'm going to make sure that my system is exactly the right size so that my chain can be periodic in that X direction. So this way, if I wanted to take an energy measurement from my molecular dynamics or whatever, then I can get a good idea of the some base energy, if you will, of this straight chain. All right, so now let's actually get into writing the data file, which all this you can do in a bunch of different ways. The data file is pretty rigid in what it needs to have. So there's a pretty specific format. If you want to see all the details of that format, definitely go look it up on the LAMMPS documentation website. It has a very good listing of everything that you can put in here. We're going to look at this, and this pretty much is most of the stuff that you would want for a hydrocarbon type system, or really most molecular systems. The only thing I'm not including in here is potential values, because I prefer to set those in the actual input file. But anyway, so let's get into it. Now the first line of data file, just like in the metallic version, if you saw my previous video on that, is just a comment. And so I just said what we have here. After that, we're going to skip a line. So I've added a new line character and then a second new line character so that there's a blank line underneath this comment. And you're going to see this several times as we go throughout this script, that there'll be an extra blank line after sections. And those blank lines are important, so don't forget those. The next section basically says how many of things are stored in this file. So I'm going to say however many atoms are stored here. And so this is going to turn out to look like something like this. There'll be a tab, and then it'll say 30 atoms. And that's essentially what you want to look for. So this is just putting in the number that is the length of my array atoms in here. And so it'll turn out something like 30 atoms. Same for bonds, same for angles, same for dihedrals. And then we skip a line and we start a new section. This section tells about how many different types of things we have. So we have two different atom types. We have carbon and hydrogen. We have two different bond types. We have carbon-carbon bonds, carbon-hydrogen bonds. We actually only have one angle type. Technically, we could define it as two different angle types, and we might have to come back and do that. But for this, at first, we've just kept it as one angle type. And we have one dihedral type. We're just storing carbon-carbon, carbon-carbon dihedrals, and not the hydrogen-carbon, carbon-hydrogen dihedrals, which you could define, but it makes a little less sense. All right, and so here is our X direction, and I am putting in this value I calculated to make sure that my X direction is periodic. So that's this calculation I did here. The Y directions, and before I keep going, you do skip a line after the types because now you're moving into defining the system. So it's the next section. Then you put in the dimensions of your system, X direction, Y direction, Z direction, and that's the end of section. Skip an extra line and move down to the main body of your data file. In the main body, you're going to have a series of subtitles, if you will, that'll have some name of thing to tell the data file what it's, what to expect next, a skipped line, and then all that data, and then a skipped line, and the next subtitle, and then a skipped line, and all that data. So that's kind of the pattern you see through here. So the first thing we're going to do is define the masses. And so type 1 atom we're saying has 12.011, so that's our carbon. Type 2 is our hydrogen, so it's 1.008. Then we skip a line and we start listing our atoms. Now this is actually not a comment. It looks like a comment in most languages, but it's not. This is actually telling the data file that these atoms belong to the molecular type. Basically, that means that they can have a molecule ID and they can have bonds and that type of thing. So it basically tells them that they belong to another structure that is larger than just an atom. So then we just iterate through all of our atoms and write them. So we have an index that we just increment. It does start at 1 and goes through the number of atoms. This is the molecule ID, which is just going to be 1 because I'm only creating one chain. And then the type of atom, which I've stored. So I'm getting atoms and types. I'm pulling the atom out of atoms, and the T is whatever type corresponds to the atom. So I can just put in my atom type, and then my atom X, Y, Z, and then next. And then when I get done with all the atoms, I skip an extra line, so that's this new line here, and then I put in the bonds, and then again, skipped line, and print out all the bonds. Now the bonds, again, they have an index, and then they have the bond type, and then they have the two indices corresponding to the atoms that make up that bond. So for the bonds, I actually stored the bond type in the bond array, and so I can just pull those three out of the array itself. Again, skip a line, and then we start the angles, skip a line, and then print out all the angles. Again, you have ID, the angle type, which in this case, I only have one type of angle, so I just hard-coded 1 in here. If we had different types of angles, we would probably store the angle type in this array as well. And then the 3 atom indices that make up that angle definition. Finally, dihedrals, again with skipped line before and after, and printed out all the dihedrals. Again, it's ID, dihedral type, and then the 4 indices that make up the dihedral. All right, so once you get through all of that, you finally have written an input file. So let's just try it and make sure it works. I'm using Julia, so you can, if you copy this code or whatever, then you can follow along and it'll look just like this. If you copy this into Python or MATLAB, you only have to make a few changes really, and you'll be able to do it very, very similarly. All right, so in here, we'll just include this, which is how you run the script, and let it run. There it goes, it ran. All right, and so you get a data file that looks something like that, where you have atoms, bonds, angles, and dihedrals. So if we open this up in Oviedo, you'll see this is what we get. So you can see this kind of back and forth structure that we used all those rotation matrices for, and you have the hydrogens going up and down from that XY plane. So I also included a very, very simple input file for LAMMPS that uses this. All of these data here are pulled from the Drying potential paper. So you can get that through your library or on the internet. And basically that tells you how all the pairs and bonds and angles and everything behaves. So we can run that with LAMMPS. As simple as this, just using the serial. Don't need parallelization for 30 atoms. And if we run that, we see it ran in 0 seconds because it ran so fast. But we should be able to open that up in Oviedo here as well. So we take a look at that. And there they are. You can see it got a little bit crooked. That's because of that angle thing I mentioned before. We are just using 1 angle definition, and probably that needs to be 2. So it got a little bit messed up. But anyway, focusing on the data file, this is how you can create your data file. I hope you found this useful. I plan to look farther into this because I'd like to make some more complicated molecules. I think it'd be very interesting and some complicated chains. So with that, I hope you found this video useful. Comment, ask questions in the comments below, and I'll see you next time. Thanks.